There's a lot of great work coming out of that lab up there in Washington, so look forward to seeing the rest of the talks over the course of the next day and a half. Continuing in the theme of climate and influences on our wildfires will be Henry Lee with the EPA. He's going to be talking about large influence of soil moisture on wildfires, biological disturbance agents, and tree growth in Pacific Northwest coniferous forests. Please help me welcome Henry. There you are. You were stuck up on me.
I did. I work for the EPA, and I lead a research project on climate change and forest disturbances and their effects on tree growth and mortality. EPA wildfire was only a topic to the EPA about 5 years ago. So my research primarily when talking about forest disturbances was drought and forest insects and diseases. And so wildfire was late. I'm late to the game of wildfire. And so my talk deals with a network of field monitoring sites that we established in the late 1990s. And I need to acknowledge my collaborators who spent most of the time in the field collecting the data. I'm a statistician, and I don't go to the field. I sit in front of a monitor, and these guys are ones that go out every month to collect and measure the trees at our permanent field sites. So according to Monty Python, and now for something completely different. So the background is that 2000 to 2021, that 22-year period was the driest 22-year period in over 800 years in the southwestern North America. And during that time period, those most recent decades, the frequency and scale of tree mortality from drought, wildfire, and insects have increased in recent decades. And there are several papers by Matt Riley who looked at the same activities of wildfire and biological disturbance agents, and he found the same things, that mortality has increased in Oregon and Washington in recent decades as well. And the question is, the interactions between drought, wildfire, and BDAs are not well understood. So there's a lot of literature looking at interactions of drought and wildfire, or drought and BDAs, or wildfire and BDAs, but there's still a lot that's left unanswered. So this is the US Drought Monitor figure that shows the drought in the last 2 decades. And you can see that from 2000 to 2022, there's a lot of years that 100% of the state of Oregon was in some state of drought. And 2015, that, according to Phil Mote, was the driest single-year drought since 1895 in Oregon. So that's sort of what the year that I always use when I compare all other droughts to that year. And according to the US Drought Monitor, you can see that 2021 likely exceeded the 2015 drought. And on top of this, the bottom line is in Western Oregon, there's tree mortality that occurred. The whitebark pine were killed by mountain pine beetle at subalpine forests in Three Sisters from 1999 to 2007. So these trees were over 300 years old. This is the first time that mountain pine beetle were able to survive at those elevations and killed whitebark pine. So this was an unprecedented mortality event. And then in 2015, the Douglas fir trees around Tillamook died due to a combination of drought and Swiss neocast. This is the first instance of tree mortality of Douglas fir due to Swiss neocast in North America. It's never happened before. And then the 2020 Labor Day fires, which we've all heard about. And then in 2021, at one of my permanent field sites, Falls Creek in Central Oregon, a cluster of Douglas fir trees died from a combination of drought, wood borers, and Douglas fir beetles in 2021. And then, nobody's talked about it yet, but in 2022, we had the large mortality of white firs, true firs from fir engraver. And you can see that when you look at the drought monitor, these events of mortality occurred during very dry years. So there's some association between drought and mortality from, a combination of drought, insects, and fire. And this, when you're looking at fire behavior, somebody has shown the triangle for fire activity, and what's the key driver of fire activity is fuel. And according to Krawczyk and Moritz, the fire activity is either limited by biomass resources in dry forests, or biomass, what we call biomass poor regions, or fire activity is limited by fuel moisture content. So east side is dry forest, and so that's east side is limited by biomass resources, and west side is limited by fuel moisture content. And so where you are, if you have biomass poor regions, you need moisture to produce vegetation, after which you produce enough biomass, then you need to follow that with a dry year to lower the fuel moisture content. But whereas on west side, if you have a biomass-rich region, then all you need is a dry year to lower the fuel moisture content. So that's pretty much that simple. And so if you look at the map of where fires occurred, 2020 was obviously the anomaly. 80% of the acres burned in 2020 was west side versus 20% east side, which is the flip of what it normally is. Normally 80% acres burned is east side, and 20% is west side. And because I guess fire was late to my research, I have a network of permanent field sites that are these triangles. And we established these field sites in the late 1990s. And what we did was we installed meteorological stations, dug soil pits, and installed time domain reflectometers to measure soil moisture at varying depths. So we have continuous measurements of soil moisture since 1998 at these sites. And I also collected tree core samples at those sites plus some other sites in Western Oregon. So this is the soil moisture data for July at depth of 20 to 40 centimeters. And the black line, starting in 1998, that's what we measured. And because I was interested in relating fire activity in terms of area burned to soil moisture, I needed to back predict the soil moisture to include the years where the MTBS had data, but we only started measuring in 1998. So I had to backfill the soil moisture data. And what you see is that in the observed time period from 1998 to 2020, soil water levels decreased 80% in that time period in Corvallis and Falls Creek. So Falls Creek is around 530-meter elevation on west slopes of Cascade Mountains. Soil moisture decreased 8% from 1998 to 2020. The period from 1917 to 1936, that 20-year period was the driest 20-year period in 620 years in Oregon, according to ponderosa pine tree ring chronologies. And that was published by Keene in 1937. So that 1917 to 1936, that Dust Bowl drought, that was the worst drought in 620 years. And my instrumental data shows that from 2000 to 2021, that 22-year period exceeded that 1917 to 1936 drought by a wide margin. So 2000 to 2021 was an extension of that mega drought that was published in southwestern North America. So this was a mega drought that pretty much was seen in the whole western United States. So this is the tree ring data, and so these are the chronologies. The black is the Douglas fir chronology, and the red is hemlock. Tree mortality from drought is not abrupt. When trees are drought stressed, it takes 30, 40 years to eventually kill the tree. And what you see in the tree rings is that the growth rates slow down 20, 30 years before mortality actually happens. And where we're seeing mortality, where we're seeing the growth declines are in the driest sites. So this is Western Oregon, which we consider as wet forests, but you can see that in some sites in the Willamette Valley, so Woods Creek, that's right next to Mary's Peak. So that's basically the Willamette Valley site. The hemlocks and the Douglas fir are showing growth declines. And you also see growth declines at the mid-elevations on western slopes of the Cascade Mountains. And on the plot on, my left, anytime you get a growth reduction of 2% per year, so first year growth reduction is 2%, next year is 4%, next year is 6%, and so on. After about 30 years of that growth decline, that's when mortality happens. And so the site which has the greatest growth decline is Tillamook. And the growth decline started in 1999. Trees died in 2015. Falls Creek, tree growth decline started in 1993. Mortality occurred in 2021. It's about 30 years. So we relate the growth to climate. This is the growth-climate relationship that I built for, and this is Falls Creek. And what you see is that the trees have been declining since 1993. And if you look at the live Douglas fir, soil moisture in the current year is the main predictor. And remember, soil moisture is decreasing And that is accounting for the decline in tree growth. And if you look at the figure on my left, when I plot the late wood against current soil moisture for June to September, it's a straight line. And the relationship between soil moisture and late wood growth, you can see that the late wood growth these trees have become more water limited starting in 1964. Before 1964, they were mainly energy limited. So some stands in Western Oregon, they're shifting from being energy limited to becoming water limited. This is a site that, remember, had 80% reduction in growth from 1998 to 2020. And you can see that main drop in growth, that was the 2020-2021 drought. Okay, so this is MTBS data, which everybody has looked at. But I'm looking at just looking at total area burned in West Side Oregon. So I'm ignoring the spatial, this is not spatially explicit, just adding up all the area burned in Western Oregon on an annual basis. And the black is the observed MTBS data, and the red is my time series regression model. And what you see is that soil moisture, current year, last year, 2 years back is is the key predictor of fire activity in terms of area burned. So you're going to get more area burned if you get multiple years of low soil moisture. So it's not just 1 year of low soil moisture, not just 2 years of low soil moisture, it's 3 years of soil moisture. So 3 consecutive years of drought. That's what's driving. Okay. But you need wet conditions to enhance vegetation production last year, and then you get soil moisture, dry conditions current year. So that's the Krawczyk and Moritz model, is that even in wet forests here that are biomass rich, you still need moisture conditions to enhance the vegetation the previous year. And there's your 2020-21 drought. Eastern Oregon is different. Eastern Oregon is limited by fuel biomass production, so you need a wet conditions previous year, dry conditions this year. And the fir engraver, so this is the Firmageddon model. So black is the observed, red is the predicted based on this mortality climate model here. And it's again driven by available soil water, but it's not just 2 years back, it's 4 years back. So you need 5 consecutive years of low soil moisture to increase mortality due to the fir engraver. Flathead fir borer, same thing. And at Falls Creek, which is 90 kilometers north of where most of the mortality due to flathead fir borer occurred, in 2021, this clump of Douglas fir trees were killed by a combination of drought and the flathead fir borer. So this is what we call the rise of the secondaries. It's killing trees in places where they don't die unless it's really a drought period. Same thing with Douglas fir beetle, same thing with mountain pine beetle. And it's driven by decreasing soil water. Every single one of these is driven by decreasing soil water. So what we're looking at is 2000 to 2021. That's the driest 22-year period in the past 700 years in the Pacific Northwest. Regional trends in fire insect activity are most strongly associated with available soil water. Regional growth declines and mortality are at where we're seeing the greatest vulnerability to fires and insects is at these lower elevations. So in the wetland valley and the mid elevations adjacent to the wetland valley. Those trees is where the soil moisture levels are declining the fastest, tree growth are declining the fastest, and mortality is starting to happen due to the flat fir borer at some of these lower elevation sites. So these, what you consider as wet forests, some of them are no longer, they're less energy limited, they're becoming more water limited and being more stressed and susceptible to mortality from fire and insects. And if you don't have soil moisture data, all you need is look at where the tree rings are declining fastest. And tree ring data is a good proxy of available soil water, by the way. Okay, I guess I'll stop there.
Questions for Henry? They're all stunned that we're in a pool.
No, John's got one.
How much of the soil moisture pattern is just tied to leaf area and evapotranspiration rather than climatic influence?
How much of the soil moisture decline is due to leaf area and temperature? It's primarily driven by warming temperatures and increasing vapor pressure deficit. So increasing evapotranspiration is basically what's driving the decline in soil moisture at these sites.
Thinking about the soil moisture declines, how does it relate to the organic matter in the soils to support it? Hold on that water.
Well, how much of this soil moisture is related to organic matter in the soils? There is a relationship in the sense that as the soils dry, there's more air, and so as the soils are drying, soil temperatures are increasing, and there's now more, the soils are shrinking, and so that there's more pockets of air. And so I guess in terms of organic matter, there's probably a lower rate of decomposition and just an increasing or decreasing ability to hold moisture in the soils as it dries. So it's sort of a spiraling effect in that as the soils dry, their ability to hold water decreases. And organic matter, I think, is decomposing at a slower rate, and so that you're getting pretty much less absorbing soils.
So you think that the water is more important than temperature, taking more breakdown?
Yes, water is by far more important than temperature.
Hi, Henry. This is Dee Dee. I think we're all looking at the question from our own perspectives, whether it be in the trees. I'm thinking of from a salamander's point of view. And especially on your last point, when you were talking about the lower elevations, I'm thinking as you go up into higher elevations where you have higher stream densities and you have the moisture, the stream effect essentially coming out from streams and the greater moisture, and that's where my salamanders live.
Yeah.
What do you know about soil moisture gradients during these droughts relative to that stream effect? Is it getting smaller?
There's a strong positive correlation between soil moisture and stream flow. Also, as you get up to higher elevations, soil moisture is not decreasing. So at my high elevations field sites at around 1,200 meter elevation, soil moisture levels that's where soil moisture levels are really not decreasing much at all over this time period. So it's only these sites that are below the snow line that we see the really big decline in soil moisture. But at 1,200 meter elevation, soil moisture levels have really not dropped much at all.
So I would suggest that there's a stream density component there where you get up in those areas that have very high dendritic networks of streams, also about 1,000 meter elevation. So it'd be interesting to look at some of your soil data relative to proximity to streams, and there are some predictions that lower third hill slope could be quite buffered from soil moisture gradients.
Could be.
Yeah. All right, thank you.